Howdy, partner, and howdy, everyone. My name is Art, and I'm a partner solutions architect here at AWS.
Hello. Welcome, Art. I am James Spencer. I am also a partner solutions architect here at AWS. Art is my co-host and one of my colleagues today. Art, I've been on this show a few times, but I'm still confused. What is Howdy Partner? What am I doing today? What is this?
Yeah, welcome to Howdy Partner, James, even though you've been here forever. This is our weekly Wednesday show where we bring in some really cool partners to discuss what they've been doing, who they are, a demo for all of us, and is a way for us to ask questions, learn more about their solution, learn more about themselves. Was that helpful?
Yeah, that triggered a few things. I remember a few things from that. So how's everyone doing? Where's everyone from in chat today? I'm from sunny Seattle. Well, sort of sunny. But yeah, today we're going to be joined by AMD and TigerGraph, and they're going to be showing us a few of their things they have done with the AMIs that they have produced. TigerGraph is specifically, I believe, going to show us something that they're doing on the AMD AMIs. AMI is basically, think of it as a virtual machine. It's basically a copy of settings with a virtual machine. So depending on your needs, if you need a graphically intensive virtual machine, if you need a computationally, intensive one, we have all different setups. AMD is powering those. AMD has their own setup. And without further ado, Art, I can't wait. Who's joining us today?
Absolutely. Thanks, James. Yeah, and it's super exciting because we have two partners today, not just one. But before we do that, we also have a really special guest that we'd like to include. So the first person that I actually want to bring out that'll help to introduce our partners today from the AWS side is Diwakar. So here we go. Diwakar, welcome to Howdy Partner.
Great. Thanks, Art. Thanks, James. This is my first Howdy Partner event, but just based on the introduction, it seems like it's a lot of fun that I had been missing out. I'm a business development and a go-to-market specialist in the AWS EC2 accelerated computing team. I know that's a lot of jargon, and I'm going to try to explain that. What we do with accelerated computing is provide a number of hardware accelerated instances that are powered by GPUs, FPGAs, custom AI machine learning silicon to solve some of the biggest compute intensive problems in the areas of high performance computing, AI machine learning, graph database analytics, and a few others. Today's focus is going to be around our FPGA-based instances that are purpose-built, custom designed with technology from our partners at AMD and our partners at TigerGraph to solve some of the biggest computationally intensive problems. So with that, I would like to first introduce Dan Eaton, who's the Vice President of Sales at TigerGraph.
Hey, thanks, Diwakar. Thanks, Art. Thanks, James, for having us. Really excited to be here.
Yeah. Glad to have you.
Yeah, we're excited to have you.
And we also have Curt from AMD. AMD is the company that powers the F1 FPGA-based instances at AWS. These are FPGA-based instances, and would like Curt to introduce himself here.
Hi, my name is Curt Wortman. I'm really excited being here today and to really talk about the partnership that we have with TigerGraph as well as AWS. If you look at my role, I'm a senior manager, part of our data center group, focusing in on analytics as well as emerging markets. So if you go, analytics is very important to us, and that's why we partnered up with TigerGraph, and we're going to have a great session today.
Great. Curt and Dan, I'm really excited to be here, and I'm looking forward to learning from both of you in terms of the solutions that we have jointly developed. One thing that strikes me right off the bat is, if you look around the world in financial institutions, in medical institutions, in insurance companies, the amount of data is exploding. And there are a number of relationships that need to be observed between all of the data so we can drive intelligence out of this data. And I think the solution that we have together here is going to solve those problems so the end users can derive a lot of intelligence from the huge amount of data that's building up. So I'm sure the audience is excited about learning, but I'm definitely quite excited to learn about these solutions today. So let's kick it off.
I have a question. First of all, what is it? FPGA? Isn't PGA like the golf thing? Or can you I don't know, explain like I'm five to me what that is?
So FPGAs are field programmable gate arrays, right? When you look at the spectrum of silicon devices that we have, from CPUs to MCUs to custom ASICs, and then FPGAs. FPGAs have a very special role to play here because they give the user the programmability at a hardware level. CPUs are great at doing things in software. They can execute in sequence, but FPGAs are hardware programmable. So the end user and the solutions builders can program the FPGA and have that design developed in hardware. With that, a few words I would let you add, Curt, since you are the FPGA expert here.
Yeah, so if you go and look at, you can see the company I'm with is with AMD. They did an acquisition that was completed about a year ago, just over a year ago, of Xilinx, and they invented the FPGA. And they were in business for 40-some years before they actually now merged in part of the AMD. So over that duration, you saw very small devices, but now we're into massive processing capability on our FPGAs. So we're talking like millions of micro cores that will be able to be stitched together seamlessly for some of these applications. And that's where AMD was extremely excited on bringing the Xilinx technology into play, because you go and look at Moore's law, we can't necessarily just scale the number of CPU cores any longer, relying upon the technology nodes. That's where we have to kind of think out of the box, right? And that's where the FPGA comes into play. We're more of a different type of computing. So we look at adaptive computing, and I'll go into a little bit more details a little bit later on, diving into what exactly is adaptive computing.
Hey, Curt. I don't know. We have some great stuff coming in the chat right now. I don't know how relevant this is to our conversation we're gonna have, but being that AMD is like, super GPU company, and we're on Twitch. Like, for example, we have some questions. One of them's asking about, is programming at the hardware level, is that similar to RISC? I don't know. Can you see the chat?
Yeah, I can answer that question. I do see the chat. So if you go and look at with the FPGA technology, we used to almost down to breadboarding back in the early days. And then over the years, we've adopted and supported compilers, which are really going to be taking Verilog and VHDL. And that was really the traditional way of writing code for the FPGA. So we've done a couple of decades of supporting those type of hardware design languages. And that's very common when you see, if you go towards more ASIC designs, and that's another acronym. If you go and look at more specialized chips in the commodity space, they're all being designed and developed really at the with using Verilog and VHDL. Now, with our latest technology, we actually introduced a compiler that actually reads C++ in, and we do translation. It's kind of with using Pragmas to kind of give hints of how to translate. So we have a higher level abstraction layers. So you can actually take C++, and a lot of the algorithms I'll show you today running on the FPGA have really been written in C++, and we're using our great compiler called Vitus to translate it into gates that get programmed, or firmware that gets programmed onto the FPGA itself. Now, I also see that there's a question about AMD moving towards ARM. And if you go and look at the different devices that we've had for part of Xilinx, is we've been a strong ARM user, and we actually have side engines running ARM. It's like ARM processor. So we had like Xilinx had the Zinc processor, which has like embedded codecs for doing video, but it's all kind of stitched together. So we moved towards more of a system on a chip type approach over the last couple of years. And even moving forward to our next generation chips, they'll have processors built onto it. And the processors of choice really depends upon what application that you're going after. So if you're going after heavy 64-bit or precision type floating point, then ARM maybe not necessarily the best type processor. That's where you may want to zero in on the AMD processor. But if you're looking for like side helper functions, then yeah, the ARM is definitely an option that Xilinx has been using for quite some time.
Awesome. That sounds great. Diwakar, where do we go from there? You're kind of our MC at the moment. You're the master of
Yeah,
stuff.
no, I think let's kick it off with Dan. I think he has some really cool stuff to share about TigerGraph and the technology they have built with Xilinx FPGAs and F1 FPGA-based instance on the AWS cloud. So we'd love to hear from Dan.
Yeah, for sure. I think just to take one step backwards to introduce graph databases a little bit. Graph databases were created because increasingly data has a lot of interconnectedness. So inside of the data, there are entities, person, place, or thing, and then relationships between those entities matter for certain data sets. And so that's why graph databases were invented, and TigerGraph is the latest generation of graph database. We were architected from scratch using C++. Our founders came from building the world's biggest graphs for social media companies and building massively parallel processing enterprise-grade databases. And what you'll see here is I'll hop into our Graph Studio UI, and we'll talk a little bit about the top use cases as I'm in here. So as I talked about, the difference between a graph database and NoSQL databases or relational databases is at the core how you represent the data and store the data. So in TigerGraph, entities, person, place, or thing, and then the relationships between those entities. So what we've represented is a really simple schema that represents a user, and a user can refer another user, which is very common for financial technology companies that are trying to build a huge network of users. And they'll have things like referral bonuses and programs to incent users to refer other users. But the downside of that is that sometimes that can lead to abuse and waste. Users will also have a device token. They'll be able to send and receive transactions, and they'll use a particular payment instrument. So very, very simple schema. With Graph and TigerGraph, the power is the fluid and flexible nature of the schema. You can update it on the fly. You can increase it. It can become very flexible based on your use cases. And then once you create that schema, you can ingest your data by mapping your data. We show how you can do that with some CSV files or JSON or Parquet or Avro. You can bring the data in, and once the data is loaded in the graph, then you have the ability to explore the graph. And what most people who are familiar with graphs they realize when you get to a large graph, it looks like a big hairy meatball. And so we've built a SQL-like query language called GSQL. We're also a contributing member to an upcoming ISO standard called GQL, which will be the first international query standard since SQL. So we're really excited about that. That should be available in 2024 as a standard, and we'll fully support that. And we think that will continue the proliferation of graph across a variety of use cases. But inside of this particular schema, again, remember you've got a user. They can invite other users. They can send and receive financial transactions and pay with a financial instrument. When you look at the data, and this is not exhaustive, but if you have millions or billions of entities, person, places, and things, and millions or billions or even trillions now of relationships between those things, visualizing it, all that data it's impossible. It looks like just a big, a hairy meatball. So what TigerGraph's query language allows you to do is to explore that data and analyze that data. And so here's a query where we walk through and look for essentially a flow of money starting from an individual user. So we're going to look at a specific user ID, and then TigerGraph, using our query language, is going to look for all transaction paths that originate from that user that circle back to the user. So they do the 6 degrees of Kevin Bacon in financial transactions. And so the financial transaction goes from an input user to another user, to another user, to another user, to another user, on and on. This will look from paths between 6 hops to 3 hops. And so when we run the query, you'll be able to see we can put in an input user and then be able to visualize the results of this particular query, looking at this circle of transactions. So you can see here in a force diagram, we've got the input user, and here are all the transactions that circle back. So they come back to that original user within 3 to 6 degrees of transactions. So this type of pathfinding is a very powerful capability of Graph, and it's enabled by our query language GSQL. And one of the really cool capabilities inside of that extends beyond traditional SQL is this concept of an accumulator that maintains the context as you're traversing all of these relationships inside of the graph. Once you begin to explore these use cases and understand how you can trace these relationships and explore all this interconnected data, there's a number of things that data scientists and users can do. They can apply SQL-like capabilities. They can do these pathfinding use cases, enabling things like everything from fraud detection in finance, anti-money laundering use cases, supply chain and distribution use cases around logistics. You can also apply unsupervised graph algorithms, and applying those graph algorithms give you the power of not even having a hypothesis, but just simply asking the graph a question. Show me how a particular user is similar to other users. Give me the top 100 most similar users. And these graph algorithms, these unsupervised graph algorithms, are in many cases computationally and memory intensive. So that's the reason why we've built a partnership with AMD and leveraged their accelerated computing libraries that make those compute and memory intensive graph algorithms give very fast time to insights, enabling our data scientists and users to be able to get results in some cases 10, 50, over 100 times faster than using a traditional CPU-based compute. So really exciting. TigerGraph, our core DNA is around being able to execute these queries at very large scale. We now have a benchmark that I think will be shared in the chat at over 108 terabytes. So over 1 trillion of those relationships between different entities on AWS. Big thanks to the AWS and AMD for their support in this new world record. And this is not it's kind of incredible. It's not where we're going to stop. We're going to keep innovating. And what we're doing with AWS F1 and hardware acceleration actually moves into a whole new category of performance for these compute and memory intensive graph algorithms. So I'm super excited. I think Curt has a demo that I, to this day, am just knocked out by the performance results of it. And it might be a good time, Curt, for you to talk a little bit about the accelerated graph machine learning library.
Dan, there's a question that I'm seeing, if you can address that. You talked about massive amounts of data and the performance that hardware acceleration can provide for the analytics of this graph database. What sort of industries and end customer types would benefit the most from the graph database in general, and then second, from the hardware accelerated graph database solution that you're providing? Do you have some customer examples?
Definitely. So 8 of the top 10 global banks' assets under management use TigerGraph, and the most common use cases for them are in fraud detection. As you can imagine, with account and transaction data, as well as third-party data sets, banks are facing a tidal wave of fraud and crime. Tens of billions of dollars per year. I personally have been impacted. I know many of you have been impacted by fraud. And what Graph allows banks and retailers and payment networks the ability to do is the ability to understand how all of the behavior is connected, and to be able to understand what is typical user behavior and what is potentially fraudulent user behavior, and be able to understand that and then act on that. And it's not just detecting net new fraud, it's actually being able to increase the accuracy and precision so that you reduce false positives, which is that scenario where you're maybe traveling to a new location or purchasing something that maybe you've never bought something like that before. And reducing false positives means not shutting down that transaction of a legitimate user who's just doing something different from the normal. And so financial crimes and fraud detection is a fantastic use case. The next area that I'd like to talk about is around customer journey and personalization. So customers, they want to be able to have relevant content. They don't want to interact with stuff that's not relevant to them. And graph-based analytics and graph-based data science help support personalization and product recommendation and churn analysis and cross-sell and upsell recommendations. And then the final area is around digital twins. So during COVID, a lot of the global supply chains were impacted, both on the demand side as consumers changed their behaviors, as well as on the supply side where vendors and the kind of interconnected upstream supply chain was disrupted. Factories were shutting down in different geographies. Prioritization based on necessity of various goods caused manufacturers to be hit on both sides, where consumers were changing and their upstream vendors were impacted dramatically. So what a number of the most innovative manufacturing companies and technology companies were able to do is build a digital twin of their supply chain, representing the components, assemblies, and vendors and price, and build a digital twin of their supply chain, enabling them to not only be able to better forecast and respond to that changing environment, both on the demand side and on the supply side, but be able to have a better pulse on their business so that their waste and overages are minimized, in some cases leading to ROIs of over $100 million US annually in terms of reducing waste and overages.
Wow, it's really impactful, right? In terms of fraud detection, risk analysis, personalization, and supply chain management. I have often received, the text messages from my bank saying, "Hey, there was a fraudulent transaction," and it's almost in real time, right? So the system has to work with low latency and real time, right? Do you have anything to say about that? How, the solution and the underlying infrastructure and all the libraries have to respond to that with almost zero latency?
Yes, it's a really great observation for those use cases that are real time, and in financial services, there's a lot of real time use cases. If you're in the payment processing pipeline, you have very limited response times, and any fraud detection you do needs to be inside of that near zero latency response time, because you don't want to disrupt the transaction. So TigerGraph is a graph database that supports both OLTP, so for transaction processing use cases where latency is very important, as well as OLAP, or analytical use cases where there's very, very large connected analytics that you're performing. And the cool thing about what we've done with AMD and leveraging AMD's accelerated graph machine learning libraries and AWS F1 instances is the ability to accelerate both the transaction processing side as well as the analytical processing side. In some cases, on the analytical processing side, we're able to accelerate things so much using F1 and AMD's libraries that we can take what previously needed to be offline and bring it into real-time transaction processing. So very, very meaningful. And then the kind of follow-on to that is for analytical processing workloads, when you can improve performance in order of magnitude or more, your analytical cluster just got 10 times or more productive. So it enables your data scientists to do more, ask bigger questions, gain insights faster, and improve the productivity of your underlying infrastructure.
Cool. Yeah, that's Dan. I mean, that sounds really awesome. I have my own questions for you in just a second. First of all, I just wanted to say, for anyone just now tuning in, welcome to Howdy Partner. We have our friends from AMD and TigerGraph joining us, and they're showing us their cool stuff. Specifically, TigerGraph is showing a use case of how their graph database platform is able to do fraud detection kind of by analyzing different hops and other things. Like I was going to ask Dan, I know we're going back a little bit. What is an accumulator? Like I was kind of, we're going back there. I'm not a data scientist myself, so I want to learn about that.
Totally. It's a good question. So when you've got person, places, and things or entities, and then the relationships between those, and you're trying to analyze that connected data, what you need to be able to do is you need to be able to maintain context and understanding as you're going on that journey, traversing those interconnected relationships. And so the accumulator is just like a brain that maintains the context as you're going off on that pointer hopping journey around your graph, so that at the end of it, it will return back the insight. On that circle detection query, it comes back and will return the number of instances of that circular transaction flow, where it starts with me and it goes to maybe 3 different people, 4 different people, 5 different people, and then comes back to me. And so the accumulator maintains that context as it's going off and traversing every single transaction, originating in that case from an individual user. Yeah, it's a very, very important capability when you're looking at graph databases and graph analytics.
Got it. Yeah, that's awesome. I love how you're describing it like as a journey, because that helps, that helps visualize what it's kind of doing. Just even without, remove all the code, remove everything. At least you can kind of have that mentality of, it's going on its path, it's doing its journey, and then it's deciding, was that journey worth it? Did it mean anything, or was it just whatever? So, yeah. Well, thank you for that. That was my 100 level question.
Awesome.
That's great, James.
And if anyone wants to try these things out, for all the developers out there, we've got some fantastic tutorials available. I'll drop some links in the chat, and you can get started. But fantastic place to get started and to learn more.
Yeah. Dan, I just really wanted to add in a comment here as you were talking about the solution. One thing that I picked on is that the massive amount of data, right? You said up to 1 terabyte of data, and the data grows quickly, right? And that's where, hosting it on a cloud environment makes a lot of sense because of all the scalability and the elasticity a solution like this needs, and the end customer data grows, right? You need to be able to provide compute, networking, and storage, right? They all have to coexist. And that's why it makes a lot of sense for solutions like this to be supported by accelerated computing on the cloud. Do you want to talk a little bit more about where is all of that data, residing? Right? Is it somewhere in the cloud? How does the interaction between the compute, which is on the FPGA, and the storage, happens? Are there any key innovations you have made there as you developed that query solution with the TigerGraph database analytics?
Yes, certainly. Good question. So customers have their data in a variety of different data sources and systems of record. And when they figure out what data they want to be able to explore and represent all the relationships in that interconnected data, they'll bring it into TigerGraph. And so we have customers that bring in data from over 300 different data sources. And then once the data is ingested in TigerGraph, all the entities, all the person, places, and things, and all the relationships inside of the data are all resolved. So if a JSON or CSV comes in, Curt Wortman, there's a string match, a partial string match, or a subgraph that looks similar to something that already exists. Curt, as an entity, will get collapsed if there's an existing person, place, or thing named Curt Wortman. If Curt's new, it'll be a new entity in the graph. And the graph itself, the relationships and the entities are stored in local disk on the EC2 instances, and then immediately hydrated into DDR RAM for very fast performance. So we're a very, very performance and scale differentiated, massively parallel processing database. So users want to be able to get results as fast as possible. And so all the data lives in DDR RAM. And then when we look at the scale that we operate, the 108 terabyte benchmark that we shared with over a trillion a trillion relationships inside of the data, that was using AMD based R6A instances in AWS. And that's something that we can accomplish with an incredible scale on an incredible budget, thanks to AWS and the just ubiquitous availability of compute resources, both compute and memory and storage. It's absolutely incredible that we can help enterprises be able to gain insights on these vast interconnected data sets with the flexibility and elasticity of the cloud. So we're just absolutely amazed by the results that we're seeing. And when we look at hardware acceleration is going to get us another order magnitude or two of additional performance beyond what we've been able to do for some of the more compute and memory intensive graph algorithms. So Curt's going to talk a little bit about some of the most common and highest utility graph algorithms that are very compute and memory intensive. And so when we look at those are things like finding communities. I talked a little bit earlier about you don't need to have a hypothesis. This isn't like a SQL query where you have to have some type of hunch. You just simply apply this graph algorithm using AMD's accelerated graph machine learning library via TigerGraph, and you can come back and it'll say, here are the communities across your 100 terabytes of data. Here's all the communities. And then you can apply another graph algorithm using the library and say, based on this one that's kind of interesting, show me the top 100 most similar. And using another graph algorithm, it'll just come up with, here are the top 100 ranked most similar. And the power of that is to be able to gain insights on something that you don't even have a hypothesis on is very powerful for data scientists.
Great, that's fantastic. And all of this is powered by AGML libraries that AMD provides. And I think, Curt, you have been patiently waiting to share your side of the story, your demo. So we'll come to you now and take it further.
Yeah, and just a quick question, Dan. You talked about that large data set and R6 instances on AWS. Like, how many, like, does that problem be solved with one just server, or do you actually need like a cluster of servers? What's the scale of that cluster really to tackle those big data analytic type problems?
Yeah, it's a really good question. So the 108 terabyte LWC S&B BI world record was accomplished using 72 R6A 48 extra large instances. So those are pretty beefy instances, but it's pretty incredible. We can be one database that manages spreading that data across 72 very beefy AMD instances in AWS, and we can spin up that workload and spin it down as necessary. So that elasticity is absolutely incredible. I mean, if you had to go and procure 78 of these beefy instances during a global pandemic, you would be very hard pressed to do that. So it was very impressive, and then I think the follow on is when you look at hardware acceleration and what's possible. I think the thing that I'm excited about is that AMD's accelerated graph machine learning library has been architected to be able to scale out for those scale out use cases and be able to accelerate the compute across multiple machines, which is very important for our large distributed use cases. Some customers' data won't be that big, but that's where acceleration is really going to be meaningful, is at larger scale, both being larger scale data sizes, but then also more intense SLAs around query response time or depth of analytics, going many hops deep, which is computationally very, very, very expensive.
And you mentioned, Dan, COVID, I believe, something about that. I just got done signing up for my free sign up here. Awesome. It's great. It looks like there's a free tier, like forever, it says.
Yes.
Which is great. And there's even a pre-built graph schema for COVID-19 analysis. I thought that was so sick. Like,
yeah, it was something during the contact tracing time period. Some of the world's biggest healthcare companies and governments were using graph to be able to help them understand this emerging pandemic.
Yeah, for sure. Anyone in the chat that's watching, we can drop it again, but there's that link for the starter kit. Definitely check it out. I just did it right now. It didn't take long. And there's a free tier forever, and there's stuff to get you started with a lot of use cases. It's great.
Yeah,
sorry,
yeah, and the starter kits are awesome because you've got pre-populated with schema and data sets and queries so that you can kind of explore. And most of us are hands-on learners, so being able to get our hands dirty is the most rapid way for us to learn about this technology.
For sure. Yeah. That's great. Sorry, I didn't mean to cut you off, Curt.
The anticipation has been building, Curt, for this demo now.
Yeah, right.
Show us how all of this works.
Yeah. So if you go and look at TigerGraph has a number of different algorithms, and they came to AMD and told us, okay, here's the most difficult problems for you to help you solve. I think there's like over 50, maybe 80 type algorithms in the TigerGraph overall library. And so we picked off like the most difficult problems that they have. And they're talking a couple different use cases. One is like a recommendation system. And so that's cosine similarity is the algorithm there. And you can see that we can have a speed up of like 96x using the FPGA. We were also talking about the fraud. I think the fraud detection use case that Dan was talking about. And with an FPGA, we can get up to about 45 times speed up over just a standard CPU. And then there's other problems. If you go and look at supply chain, where you want to be able to have like the FedEx routes optimized, or UPS routes, or any type of things like that. That's where the maximal independent set algorithm comes into play. And the FPGA accelerator can go 250 times. So definitely a couple order of magnitude there. And then the last one is like entity resolution, that if you're getting tons and tons of data, you have to figure out what, if there's a typo, and that's where the Levenstein distance is going to be used, and one of the other algorithms. So you're seeing like a roughly 100 times speed up on the FPGA accelerator. And actually, I have one of the accelerators, just a show and tell type thing. This is what the accelerator looks like that we actually plug into the servers. So it's like a PCI Express. You can see at the bottom, there's actually a PCI Express connector. And you plug that into a server, and a lot of times the servers have like multiple different PCI Express slots on the motherboard, all the way up to like 16 or 18 slots on a given motherboard for some of the higher end servers out there. So and then you have blast air through, and then through PCI Express, they kind of back and forth between the processor to be able to move all that data back and forth. So I think that that's a way that we can actually scale. So you can collapse in terms of size as well as the power efficiency. If you can think about how do we actually have sustainable energy, where you actually can collapse a lot of those workloads into smaller, compact hardware, and or scale out in terms of the business problems itself as we kind of increase the databases. So there's what is an FPGA. I think that's another area. Within that particular card, there's actually sitting inside one of these chips that we have, and it's really going after adaptive computing. So what's how does that differ from like a CPU or MPU or TPU? So what we've really come up with the FPGA technology is the capability to have millions of different elements, lookup elements built into the FPGA. And we have massive amounts of interconnection that is fully programmable. So then you can build out these different functions that reside on the FPGA, and then stitch those together. So different size functions, and as well as locality to memory. Within the FPGA, we use a lot of like small, tiny caches. So it's built into the actual logic flow itself. We don't have to run across the chip and out into like a cache to get the data. So that really saves a lot of energy by kind of moving the data access into memory next to each other. So it's very, very fine-grained technology there. And then in terms of the throughput, you can look at running like 400 gigabytes of data through some of the data paths that we're talking about. So lots of parallel engines. So this is kind of depicting just really a serial fashion. But think about the parallelization. So you're talking like thousands of parallel streams running alongside each other, crunching on the data as it gets through. And that's how we do a lot of the times the acceleration, is we able to load up what Dan was talking about, chunks of that database in our local FPGA memory. We have DRAM chips built right into the cards themselves. So we partition that database across multiple different cards and then access in a parallel fashion to be able to crunch the data and then return like the summation or accumulated values back to the host processor. That's then reported up to the application itself. So that's kind of these small micro engines that can be programmably stitched together. That's what makes the FPGA so unique and different. It's a super fine-grained architecture versus if you go and look at AMD CPUs, you're talking on the order of like 128 cores. But if you go and look at some of these, we're talking millions of these fine-grained elements built into our FPGAs. So we have the capability to really address these parallelized applications super. So that's kind of, and I'll kind of now switch over to the demo itself. So we fired up an instance. So basically, you can go to your AWS EC2 instance and create an instance. And what I've done ahead of time was actually loaded up the software so you can download the free trial software from TigerGraph, install it. And with the TigerGraph capabilities, they have the capability to have a user-defined function, UDF. And that's where within that special API call, we actually farm out the pieces of that data that connect over PCI Express to the FPGA accelerators. So in terms of the demo, if you go and look at, we have built up this fraud database, and we've actually loaded up with 1 million or 10 million features. And so we did that ahead of time. So the application, and if you just loading and running some of these basic operations, I think Dan was talking about a few of these inquiries that you can actually run. The first thing you want to do is to be able to load through into your schema the data, and so you're ingesting data from like existing CVS files. And let me just crack open a terminal with the CVS itself. So this is it's a very large file. So, but I'll just kind of show you what the format that file looks like. Let's see if I can expand my screen a bit. So this is kind of just the first 10 lines of that ingest CVS file. And you can see that you can see people's names, their date of birth, their address, their emails or phone numbers. So these are all kind of attributes that get pulled into this particular database. And so what we're trying to do is try to find similarities, basically looking at the communities that are being ran. So this is kind of the first piece. The second piece, let's just switching back to, is that within this graph, this is the Graph Studio that Dan was sharing before. It's very GUI oriented, that you can press different queries as well. But you can write all these type of queries in either, and I'll show you in the next slide here, is you can actually create for data scientists a Jupyter notebook and pull in and connect to all this underlying data. And so this is what this demo does, is it actually goes off and grabs that $10 million data set of different loan applications. Let me just run that on that EC2 instance. It's going to take a few minutes to kind of run, but just let me walk you through what we have here. So if you're familiar with Python, we're bringing in a bunch of different Python libraries, including like NumPy, Pandas. There's the sklearn, which is more for machine learning data kits, as well as XGBoost, which will do a lot of the classification of the data. And so this is on non-connected data, and we're going to present out a confusion matrix, which will tell you, okay, if you don't have a graph, then what is the chances of it being a false positive or a false negative? So the success rates will come through part of this. So it's being processed, all these functions. Let's skip down a little bit further. What it's done here is it loaded the data sets and formed the features. So we interacted with that TigerGraph database where you have 10,000 features that you're going to be analyzing to see whether it's fraudulent or not. And so we're creating a data frame, and what we're pulling out is, okay, we're going to see if you use these certain algorithms, which algorithms will provide the best level of accuracy, as well as what's kind of the resultant of the data sets using kind of traditional ways of doing machine learning. And there's going to be different functions. I'll go down a little bit further to pull that out. And so if Genie and OC, AUC as AUCPR, kind of the common ones that have been tackled. And the confusion matrix without the graph features are showing that in this example that you're getting a lot of false negatives as well as false positives. So it's actually the predicted level is not getting the best results. But when you go to the graph where you have connected data, then you can employ certain other features or create features. So you're actually doing feature engineering. And what feature engineering is, it's like we're talking about connected data using the graph, and feature engineering is kind of running certain algorithms that is then populated into the analysis. And so the first algorithm will be like PageRank. Everyone probably have heard of Google. They use PageRank to kind of figure out the popularity of the web pages, and that popularity score factors into what you see coming out of the search. So PageRank is very commonly used. We actually accelerate that one as well. And then the second algorithm that is being used is going to be called Louvain modularity. And so it's not just looking at like how popular, but it's like trying to figure out the connectedness between who's in the community. So if you can think about a certain community is like who's in your neighborhood, and that would be one type of relationship. Because of based on the streets, and versus if you live across the country, you may have less of a relationship. So there's different aspects in building up the communities. And you can see here that the confusion matrix kind of showing the false negative and false positive is much better. So you actually want a very high value here, as well as a very high value here, and low values in these other confusion matrix quadrants. And it's scored much better with taking that PageRank as well as the community detection. You can see that PageRank actually provided the best measure that we actually have done with the graph, followed by community detection. And it outweighs the first digit of amount, which was being used with XGBoost for some of these other ones. So this is kind of also showing that with graphs and using that extra feature engineering information, that our accuracy increases quite dramatically. You can see that with the data set itself, it improved over 100% in terms of accuracy. So that's very meaningful. If you have like a call center or a data center or your data scientist, you don't want to spend hours upon hours kind of sifting through. It's like, oh, that's bad data. Oh, that's bad data. That's bad data. You want to be able to, it's like, that looks like a real fraudulent activity. And having the data scientists dive deeper into the ones that make a lot of sense. So you're throwing away a lot of the false negatives and just going towards the ones that are being analyzed here. So the improvement will increase not only the connectedness, but also giving you a lot of improvement. So this is all being ran on those algorithms, and this is kind of showing the power of graph over a non-graph featured engineering data set. Now, where the FPGA comes into play is, let's switch over to this next tab, is so we have the results with and without the FPGA, and I got to show the speed up. Let's just press run here. That will kind of launch and run these. Now, what this does
Curt,
is...
I have a quick question before you
go ahead.
jump into those details. So you talked about training the graph database model, right? And in the machine learning domain, there are two aspects of getting results out of a machine learning algorithm. One is the training aspects. You feed it a bunch of data and train the model, and then you later use it for inference by providing the actual input and looking for the output with certain accuracy and level of prediction. In the graph database machine learning domain here, what does training a graph database model mean? Can you allude to that a little bit?
So you are kind of going back and doing still machine learning. So it's still that data scientist context that you want to test out how good your algorithm is, right? And so what you have to do is you want to throw a ton of data at it, and then determine by throwing in some known bad data and testing that. So it's almost labeled data. That's what a lot of times your training sets are, to kind of refine what your models are. Now, when you're throwing that data, that good data versus bad data, what's meaningful and what's not, right? And like the color of my socks don't really matter very much if in regards to a fraudulent activity. But if more like, am I logged on to the internet or not? That might be much more meaningful. So you want to be able to zero in to the really meaningful data, and that's where the page rank as well as the community detection through Louvain is trying to pull together and identifying what's meaningful.
That's right.
And then to refine those algorithms through the training sets.
And those algorithms are refined because through the library, you have already pre-trained these models, and they don't need to be trained by the end user for their specific use case, correct?
Yeah, to chime in a little bit on the graph algorithms like Louvain and general PageRank, those are unsupervised algorithms. So you can apply those to the data set and get the results without going through a training process. And one thing that Curt is also showing is how these graph-based features that you get from running these unsupervised graph algorithms can then be fed into existing machine learning models for product recommendation or fraud detection, and can enhance those the kind of quality of those models. So in that confusion matrix, you're seeing false positives and false negatives both improve, which is great. And then I think that going to the spirit of your question, which is going to go beyond where we are today, but looking forward into the future, not only can you take these unsupervised graph algorithms and improve your models, your existing machine learning models today, there's also another way that you can use graphs, which is for graph neural networks. And so graph neural networks will be able to kind of learn those complex patterns and generalize better, kind of extending even beyond the capabilities of these unsupervised graph algorithms that are incredible in terms of their understandability and how they will improve and enhance existing ML models. But GNNs for certain use cases will even improve things further for those broader tasks where you've got really complex patterns and incomplete data, and you want to be able to generalize going beyond this. So, Curt, I don't mean to go off on a tangent, but I love these topics.
No, thank you, Dan, because it is very important that we do want to highlight that a lot of these algorithms, because of the data size itself, is going to be unsupervised learning, right? And that's where you want to not have data scientists writing all these rules, and you actually want to use techniques to unsupervised, basically throwing compute cycles at the problem itself to kind of extract where the valid data is.
Great, thank you both.
So right now it's running on the CPU. You can see that it takes a few minutes to actually run on the CPU, and it'll be much faster on the FPGA once we get down there. But we can take any questions right now, and I can kind of come back and show you what the results are. I did run this previously. It looks like it cleared the results, but in about 10 minutes, we should have the results back, kind of showing what the CPU, how many seconds the CPU took versus looking at the FPGA. And so just give us a few minutes for it to run. So maybe it's a good time to kind of answer any type of questions. I'm not sure if you have any questions so far.
Yeah. Hey, Curt. Also, this also might be a question for Dan too. But you kind of mentioned like the benchmark of the actual times is that the performance, increases. But can you paint a picture of context of like what the comparison was like, before, and then after? This run you said will take about like 10 minutes or so. But in terms of the performance of things that you've run before on F1, what's the time comparison that we can see or expect?
Yeah, I can give the kind of high level, and Curt can probably explain more details. But like this algorithm that Curt's showing, when you're looking at Louvain community detection algorithm, it's a pretty widely used detection algorithm that iteratively goes through optimizing modularity, and it merges the nodes into communities and then forms a new graph from those communities until the modularity kind of converges. So it's very iterative. It also causes, because of that, those new communities and the graphs that get formed, it causes the memory to kind of balloon through a lot of implementations to optimize the response time. So what we're experiencing and seeing here is we can not only get the results in order of magnitude plus faster, but we shrink the memory compute by, Curt, I think it's like 5x on the runs we're seeing.
We had some runs that we saw about 70% memory savings by running on the FPGA. Because if you go and look at a CPU, a lot of times you have to take that data chunk itself. So that will be in one piece of the memory. but you still need a lot of server memory to actually run the algorithm to do the iterative portion. And so we saw roughly 70% memory savings. So cut it down to about 30% of your overall memory to be ran on the FPGA. So that also means that, okay, now it's down from 70% to 30. You can run a 3x type data set on that given single server if you need to. And so maybe answering one of your questions, Art, is like what were kind of the data sizes that we were analyzing? So we actually benchmark all the way up to 900 million transactions. So this is just a small data set, basically 10 million, a data set of like 10 million type entries, but we ran all the way up to about 900 million transactions through it to see what that is. So a lot of times on a single server, you can't really tackle that type of problem, and you have to span across multiple servers. And these servers you max out in terms of RAM. So we're talking like half a terabyte to a terabyte of RAM per server across multiple servers. And that makes the servers super expensive themselves. And so because of the memory content, it's not just the AMD processors, but the cost of the actual DRAM chips that go into these servers are a very, very big portion. So this is a way that we're kind of optimizing that by kind of pulling a lot of that and partitioning that data on the FPGA and not burdening the CPU and the memory on a per server basis by kind of offloading all that onto the FPGA.
Yeah, and Curt, just to add to that, right, if we distill down the three key benefits of running it on FPGA-based instance is number one, the performance boost, the less memory requirement, and third, latency. And then it has substantial benefits for the end customer in terms of the real-time results they can get, but it also implies what cost they have to pay for the infrastructure deployment. And higher throughput and less memory required brings down the cost of running these millions of transactions. So it's hugely important that we get high performance as well as algorithms that are optimized, and FPGA-based instances are able to do that.
Yeah, and I think that's a really good concise summary, and one application of that summary is data scientists being able to ask questions that they previously couldn't.
I have a question. So for these instances, where can we find these? Is there a marketplace? I was able to get some TigerGraph marketplace stuff from Dan. Are these going to be in the marketplace, or how are we going to be able to leverage these, like when we want to spin them up? Is there a specific way?
So if you look at AWS EC2, there's different instances there. For the FPGA, we actually have an F1 instance, which is a special server that has FPGA cards populated into. So from a hardware perspective, you can load up one of the EC2 instances and select the type of instance types you want. You can basically select the instance type and just search for the F1 instance.
Yeah.
Got it.
So maybe James, maybe I can take over and talk a few minutes about the instance types that we have on the EC2 while Curt is still running his program. Curt, is that okay if I take 5 minutes to talk about the instances? Because that's really a great question, right? At AWS, we provide a number of hardware accelerated instances, and the proper choice of that hardware accelerated instance depends on the use case. I'm going to share my screen and a couple of resources here for folks to look at. Let me drop another one here on the chat. Can you all see my screen at the moment?
Not yet. We still have Curt's up. But
okay,
oh yeah.
Sorry. So for the audience, you've heard EC2 quite a few times today. I just want to make sure everybody understands what that means. EC2 is Elastic Cloud Compute on AWS. What that means is we provide variety of compute elements. And the benefit of running that on the cloud is all the elasticity, the scalability, the worldwide regions these compute elements are available in. And we categorize the AWS EC2 compute capabilities in a variety of instance types. So we have general purpose instances, compute optimized instances, memory optimized instances, and the topic of discussion today is accelerated computing instances, which are powered by hardware accelerators such as the FPGAs. So at AWS, we have a variety of hardware accelerated instances that are powered by GPUs, custom ASIC for AI and machine learning, and then, as we have discussed along in this presentation, the FPGA-based F1 instances. You can find all of the information here at aws.amazon.com/ec2/instance types. What I want to focus on is the F1 instance, which is powered by Xilinx VU9P FPGAs. It's paired with a CPU, with NVM SSD storage, and enhanced networking. Storage and networking and compute go hand in hand. And in order to provide that high compute intensive workload capability, all of this has to be tied together to deliver the compute in the most efficient way. For F1 instance, it's powered by Xilinx Vertex UltraScale Plus VU9P FPGAs. It's one of the UltraScale Plus FPGAs from the family, and Curt has talked about a little bit already, and is going to touch base on that in a few minutes as well. A few other things that make an instance are DDR memory, PCI Express for interfacing between the CPU and the FPGA. The FPGA here has 2.5 million logic elements. And if you remember, Curt was showing the picture of logic elements on the FPGA. It's counted in millions, and each one of those can be configured to create a logic and a hardware program on the FPGA to deliver the compute capability. It has DSP engines. The FPGA-based F1 instance comes in a variety of sizes, and we measure that by how many FPGA cards are on a server. So you remember Curt was showing the hardware earlier with PCIe. Each one of those PCIe-based hardware goes into a server, and how many are on a single server rack determines the type of instances. And depending on the compute, the memory requirements, one would choose the right size of the FPGA or F1 instances. So we have F1 2x large, 4x large, and 16x large, and they differ in terms of the number of FPGAs they have, the amount of CPU capability, the integrated memory, instance storage, and networking performance. So depending on the workload and the end performance that one is looking at, there would be a choice of the FPGA instances. Now, talking a little bit more about the FPGA instance itself, we serve a variety of workloads with F1 instances. Some of the prominent ones are graph database analytics. There are use cases in the genomic space, media entertainment, and so on. And all of this is really easy to get started with. Curt earlier showed an AWS console where you can spin up an F1 instance, and that is powered by Amazon machine image, which is also available. There are example codes that are available on the GitHub. Xilinx tools to start up an FPGA instance are available through the GitHub as well. And we talked quite a bit about the performance and the benefits of the FPGA instances today, right? And just to reiterate, for high performance computing, amongst others, FPGA instances are a good fit. For workloads in graph database analytics that are dealing with massive amounts of data in relatively short span of time, require huge amount of capability in terms of compute, and FPGAs deliver that. Same thing in genomic sequencing and other workloads. As the benchmarks that have been shared, we'll see that FPGAs provide a massive bump up in terms of performance over CPUs, because CPUs are doing the software code execution, whereas in FPGA, you're doing the hardware acceleration of the same algorithm. And then generally, I would say FPGAs are perceived to be difficult to develop with, but with all the effort that we have put into building the solution and providing a development environment with tools from Xilinx, with tools from AWS, and then solution from TigerGraph, it's really easy to adopt an FPGA-based solution. So I'm going to share this link as well, and you can look at all the resources we have regarding FPGAs-based F1 instance, some of the other technology partners that we have, including TigerGraph here, and other resources to get started with F1 FPGA-based instance as well. So hopefully that gave you an introduction about Amazon AWS EC2 accelerated computing instances and where F1 fits specifically. It serves a very unique purpose for computationally intensive workloads like graph database analytics. And yeah, you have the information at your hand with the resources that we have shared.
Got it. That makes sense. Like, so that makes it even easier than having to go. Marketplace is already easy enough to use. This makes it even easier because it's just, you can do this just as part of spinning up a EC2. That's what you're saying? You just select it and throughout the wizard or the console if you want.
That's right. And what
Awesome.
Marketplace does is it provides a special AMI for the specific solution. So you can, connect the dots here, right? There is a solution library that TigerGraph has developed that's available through the Marketplace. So you spin up an instance, bring that library in, and then when you invoke all of that together, you have the solution running on AWS.
Got it.
So just to be clear, the F1 based solution is not available on the Marketplace yet. It's something that's going to come out in the future, but you get the idea on how all of this can work out. For now, if you need the solution, Dan, Curt, myself are the key contacts. You can reach out to us and we'll enable you and make sure you get up and running.
For sure. Yeah, we'll need to drop your emails and stuff a little bit later. But one last thing for me, I thought it was great. You said you started and you said it's very easy to get this solution going because of AMD, because of this, because of, I love that abstraction, like because of the 50 layers of abstraction, it's easy for you because we've done all the hard stuff. And I'm like,
exactly.
That didn't sound very simple, but I'm glad I'm on the simple side of it, I guess.
We make it simple for you.
Yeah.
So with that, I'll hand it back to Curt to continue with the demo.
Oh, shoot. Okay.
So we have some results here. Let's just go to the top. So we ran the data on the CPU only just to kind of see how long it would actually take and how much memory it would consume using the CPU. And then we actually ran it on the FPGA. And the first step that we need to do is take that data. And so we're extracting from that graph only the data that we want to analyze. So that's the vertices and edges that we were talking about before about this on the schema side. And it takes it loads up that partial graph, that partition onto the FPGA, and then drives it into the FPGA and execute it. The first thing we want to do is we support different algorithms. So we have to kind of load in the FPGA image and then load in the data that we'll be processing. And so we can switch between different algorithms pretty much on the fly. It takes a few seconds to kind of load in that customized algorithm into the FPGA and then to run and execute. So you can see here that it took about 390 seconds to run on the CPU versus 45 seconds on the FPGA for this small data set. We want to be able to take much so, like 10 million is small in relationship. So you can see the speed up here is roughly 9x, almost 10x. And we can see here the memory reduction. It really depends on the actual, we're not using a lot of memory just because it is a small data. A lot of times we actually save when that goes into much larger data sets. So it's more focused on the acceleration time because we have tons and tons of memory on this particular instance here. Okay. Any further questions?
Not from me at the moment. Anything in chat? Mind zooming in a bit? Yeah. Curt, if you could zoom in maybe a little, one or two. Yeah. Oh, they're beautiful.
That's a little easier to see.
Runtime of Louvain. Oh, okay. And this was all done, and like you said earlier, this was all done with libraries that AMD had provided?
Yes. Yeah.
Okay, cool.
So we build the C++ libraries that get loaded into the FPGA, and then we tack on to the API that TigerGraph has called UDF. So we open sourced all these C++ algorithms that you can actually compile. Some of the customers that we've engaged with want to kind of tweak because they're necessarily not the exact algorithm they want. They may have variations on the window size or some other aspects. So we open source all our libraries. You can go onto GitHub and download the actual C++ code that then is translated into gates and loaded onto the FPGA itself.
Cool. What is the GitHub link? Can we search just AMD, or what would you have to search for that?
So let's see. I have it here. So we have the AGML, which is the documentation. So that's kind of talking about Louvain, cosine, maximum independent set. So I can see. It's a good way to kind of send that through. But then in terms of the GitHub, we have the Vitus libraries. And
okay,
the Vitus libraries itself is actually where the code resides. And inside Graph, we have different algorithms. If you go to an L1, there's the similarity. So we have cosine, as well as a bunch of L2 based ones, predefined type kernels. So we try to go off and compile that ahead of time, so you don't necessarily need to go off and spend a bunch of time writing C++ code for the FPGA. We actually provide the AGML library that you can just download the precompiled kernels onto the FPGA itself. Or if you need to do something custom, the original, the source code is there to modify.
Then we have there's a comment in the chat saying there might be something that internally would be beneficial, improve cost efficiency of AWS RoboMaker. I'm not really familiar with what AWS RoboMaker is. Do you know? Could you speak to that, or anyone here?
Yeah, I think I would like to take that internally, James. I would like to understand, the thought behind RoboMaker. Certainly, F1 instance can be used there, right? But what specific piece of analytics in the RoboMaker? Yeah.
Okay. Yeah, that's cool. That would be cool to think of, because I don't really know much about it.
Yeah.
So awesome. All right, cool. Dan and Curt, or Diwakar, is there anything else that you wanted to show us today?
No, I think probably that's it in terms of the demos, right? But I mean, maybe we can reiterate the benefits a little bit more from why graph database, right? Why TigerGraph solution, why we need FPGAs, and why we need FPGAs on the cloud to enable all of this. I really liked, James, how you sort of put it together, right? Hey, it's not easy, but we have done all the work, right, across the teams at TigerGraph, AMD, and AWS to package it in a manner where our end customers can consume it. So maybe Dan, if you could summarize your take on the graph database, TigerGraph, and so on, and then we can sort of build on that to make it firm for our audience.
Yeah, certainly, and I think it's a great point, Diwakar. We're standing on the shoulders of giants. On the TigerGraph side, we are benefiting both from all the innovations in computer science and mathematics that have led us to today. The use cases are many. In any case where you have a lot of interconnected data, and you really want to preserve the native shape of that data, where all the relationships between the entities are important. So fraud detection, personalization, customer journey, digital twins, cybersecurity. There's a number of use cases where you've got a lot of interconnected data. And when we look at why TigerGraph, TigerGraph is performance and scale differentiated. So when you're performance and scale differentiated, you can't stop innovating, because that's your differentiation, is performance and scale. And to get even more performance and be able to solve even bigger problems, we have to leverage hardware acceleration. And AWS and AMD have been fantastic partners to help us continue that innovation.
Great. And Dan, I think what I love the most in terms of your narration here is a statement that you made earlier, right? It gives data scientists the capability to ask questions that they thought they never could, right? And also, thinking about hypotheses that you just didn't know could be answered, and having that capability with this graph database solution is immense. Now, I know there are a variety of solutions where variety of infrastructure options this could run on, but FPGAs provide a bump up in terms of performance and latency, right, that customers are looking for. So combining that with the power of the solutions that AMD provide in terms of the graph libraries and the scale and elasticity and the geographical presence that AWS has, I think our customers really have a great solution in the graph database analytics space for in a number of industry verticals, let's say. Curt, anything to add from your side? I think he just went off screen here.
Yeah, he might have lagged out. I think he was a little bit frozen earlier.
I think we got him back.
Okay, cool. There he is.
Cool.
Curt,
I was just asking for your parting thoughts.
Yeah, sorry about that. So yeah, I think there's going to be continued innovation from the AMD side that will continue to invest in heterogeneous computing, and that's where the FPGA is very important, and tailoring, I guess, future data center hardware to really take and tackle those big demanding problems for data analytics. So I'm very excited. There's definitely a lot of new hardware that AMD is working on, and we're going to be very excited to kind of release that into the public for these new particular hardware devices.
Awesome, team. Yeah, and I think, Diwakar, you mentioned, all the different types of industries that you see. My personal interest is in healthcare life sciences, and I've seen the case study with Illumina using the F1 instances, and genomics is really compute intensive. So I know there's talks of having them on the show as well, and I think it'd be really great to see that in action as well, and kind of see what the end-to-end looks like, because there's a ton of data involved, a ton of just information there, and I think, yeah, I'm really excited to dive into this.
Great. Thanks for calling that out. It's a great use case.
Cool. Awesome, team. I'm not sure if we have any last questions in the chat. Let me just double check.
Nothing for me that I can see. As always, we want to finish up with doing our plugs and, of course, our famous AWS surveys. That's what we're known for. One of our many things. So yeah, so if you want to connect with any of us or AMD or TigerGraph, go ahead and check us out on LinkedIn. I'm going to drop the ats in the chat here. There's some of them. That's all of us. And then here is TigerGraph and AMD. So yeah, if you want to learn more, you can talk to us on there, connect with us. Not just learn more, but anything that you could think of, just either be curious, you're interested and want to get started with TigerGraph and AMD, see what you can do for your company, bringing in their solutions, see how they fit for you. Definitely check us all out. Also, we have Art. Would you mind dropping in our survey? Like I was mentioned, I love our surveys. And for anyone else on the stream right now, if there's anything you'd like to plug, either personally or professionally, it could be either. You could be a TikTok famous. I don't know. If you want to go ahead and drop something, that's cool. We can do that now. Nobody?
It's just you, James. You're the only famous one.
I'm the only one. No, but yeah, cool. I mean, thank you all for coming. Hope we learned something new. Check out those links. Check out the TigerGraph links, the AWS Marketplace. Try out the F1 in just the EC2 console. And we hope to see you back next week. Who's going to be here next week? I believe it is Kaylent is going to be joining us next week. And I just want to one last time say thank you to our partners, Curt and Dan, and also my coworkers, Diwakar and Art. And with that, I guess we can just say, please fill out the survey and howdy. Happy trails to everybody. Thank you for showing up.
Thanks, everyone.
Thanks, everyone.
Yep. See Art.
Thanks
See
for
James.
hosting the great show, Art, James. Bye-bye.
Cool.
Yep. Bye.